Hello, my name is Me, and I am representing an ultrasonic transducer. So first, we will talk about what is an ultrasonic transducer. Then we will talk about its types based on the sensing element. Then we will see its working and applications, and in the end, we will talk about the advantages and limitations. Ultrasonic transducers convert electrical energy into high-frequency mechanical vibrations and vice versa. These vibrations are typically in the range of 20 kHz to several megahertz and are used in a variety of applications. The ability of ultrasonic waves to penetrate solid materials and provide detailed information about their properties has made them an essential tool in many fields. Devices are mainly used to measure distances, and we'll see how. So it has two parts, a transmitter and a receiver. In the most standard configuration, they are placed side by side as close together as reasonably possible, as we can see in the above figure. Sound travels in a straight line from the transmitter to the detected object and back to the receiver. There are also transducers where the transmitter and receivers are integrated into a single unit called transceiver. The formula to calculate the distance is half into t into c, where c is the speed of sound in the medium, t is the time gap between transmitting and receiving the ultrasonic wave, and we have a factor of half as the wave traveled twice the distance to be measured. Now we will see the types of ultrasonic transducers based on the sensing element. First is piezoelectric, then magnetostrictive, and then capacitive. So on the left, we have a design of a standard piezoelectric transducer. We can see that there is piezoelectric layer between the matching layer and the backing layer. When alternating voltage is applied to the electrodes, the piezoelectric material contracts and expands very rapidly, causing it to vibrate and generate ultrasonic waves in the surrounding medium. Conversely, when ultrasonic waves are incident on the piezoelectric material, they cause it to vibrate and generate an electrical signal that can be detected by the electrodes. The backing material absorbs any unwanted vibration to improve the accuracy, and the purpose of the matching layer is to reduce the reflection of the waves and to improve the coupling of the transducer to the medium. On the right, we see a piezoelectric micro-machined ultrasonic transducer. They are constructed using silicon wafers and thin film piezoelectric materials. They offer several advantages over traditional piezoelectric transducers, including higher sensitivity, lower power consumption, and its compatibility with microelectronic circuits. So the second one is magnetostrictive ultrasonic transducers. Magnetostrictive effect is a property which is observed in certain materials that causes them to change shape when subjected to a magnetic field. So we apply an alternating magnetic field to the magnetostrictive rod, which in turn expands and contracts at the frequency of the AC signal applied, creating ultrasonic waves. Conversely, when an ultrasonic wave strikes the magnetostrictive rod, it causes it to vibrate, which generates a magnetic field. This magnetic field induces a voltage in the coils, which can be analyzed to provide information about the ultrasonic wave. They have some advantages over piezoelectric transducers, including a wider frequency range and higher power output. However, they are also generally more complex and expensive to construct. So the third one is capacitive. Here we see a micro-machined capacitive ultrasonic transducer. The basic element of a C-mute array is a parallel plate capacitor. One plate is fixed and the other plate is supported by a flexible membrane. In receiving mode, an ultrasonic wave causes membrane vibration and a change of capacitance which is detected. And in transmitting mode, an alternating voltage is applied between the membrane and the substrate plate. The resulting electrostatic forces causes vibration of the membrane, sending out ultrasonic sound waves at the frequency of modulation. First application is non-destructive testing. We can determine the location of a discontinuity in a structure by accurately measuring the time required for a short ultrasonic pulse generated by a transducer to traverse the thickness of the material, reflect from the back of the structure or the surface of a discontinuity, and return to the transducer. In this video, we can see that the output of the transducer on the oscilloscope. As we move the transducer over the surface of the structure, we can see that at the point of discontinuities, the output changes accordingly. Ultrasonic transducers also have numerous applications in medical imaging, where they are used to generate and detect ultrasonic waves in the human body. This is known as ultrasound imaging, which is a non-invasive and relatively safe image modality compared to other imaging techniques like X-ray or CT scan. They are also used to detect objects underwater, which is basically sonar. Piezoelectric transducers are used extensively in underwater sensing applications. They can also be used for underwater communication and marine biology research. They are also used in distance sensing applications such as in parking sensors, where they detect the distance between the vehicle and the obstacle. And they are also used to measure level of liquid in a tank or a container. It is also used for flow measurement. As we can see in the video, there are two ultrasonic transducers mounted on the pipe. Both can generate and receive ultrasonic sound waves. The water is flowing from left to right, so the ultrasonic wave generated by the right transducer will move against the flow of liquid, so it will take more time to reach the left transducer, while the ultrasonic pulse generated from the left transducer will reach the right transducer rather quickly. Using the time difference between the two pulses, we can calculate the velocity of flow and the flow rate. This same technique is also used for blood flow measurement. So first, the strengths of the ultrasonic transducer. They are unaffected by color of the object being detected. So it doesn't matter if the object is opaque, transparent, or translucent. Second is that its minimum and maximum ranges are quite flexible. They can also make many measurements per second. And as there are no rare materials required for the construction of piezoelectric transistors, they are also inexpensive. And the last one is they can also be used in dark environments. Now the weaknesses. As the speed of sound is dependent on temperature and humidity, so the environmental conditions may change the precision of the measurement. Also, the sound is dependent on a medium of some sort, so ultrasonic sensors do not work in vacuum. Thank you.